Another aspect of poroelasticity is that a poroelastic material is also a viscoelastic material. So when we talk about viscoelasticity in terms of solid materials, what we're talking about mainly is a couple of things. There's a couple of properties of viscoelastic materials, and that is the elastic modulus is a function of rate. Okay? So if I go to the lab and I measure the elastic modulus as I load it really slowly, I will get one measurement. And if I load it quicker, I will get another measurement. And if I load it really fast, I will get another measurement. Typically, as drawn here, so increasing loading rate or strain rate will cause the elastic modulus to stiffen. So this is one property of a viscoelastic material. And another property of viscoelastic material, and it's really a different way of saying the same thing, but the measured elastic modulus is a function of frequency. And the reason that we say that is because typically when you measure elastic moduli in the field, you do it with sonic log, right? We talked about last time a little bit about how to do that because there's a relationship between the elastic properties and the sonic velocities. Okay. So because the material is viscoelastic, though, you have to be very careful about the interpretation of the data, because the frequency at which you propagate the sound wave through will give you a different reading back on the elastic modulus. Okay. And an example of this is here. So in the, let me see if I can zoom. So here what you see, the solid curves are pressure volume. So in this case, they went to the lab and they had a piece of rock and they put it under hydrostatic confinement, typically in a fluid bath, right? So they put it in a bath of fluid and they ramp up the pressure on the fluid and they squeeze the rock, compressing it. And they measure the volume change. Okay? And so the slope of these is what? The slope of these lines is what? Huh? It's the bulk modulus, right? So the solid lines represent the bulk modulus or you know, these pressure volume relationships for scenarios exactly what I described. Go to a lab, put it in a pressure bath, squeeze it. Okay? The other lines, the smaller lines, these guys represent what he calls dynamic, but understand these are from ultrasonic measurements. Okay? So these are the elastic moduli. Those small lines are the elastic moduli that are measured from ultrasonic measurements that are performed at the same time that the quasi-static tests are, you know, the tests are taking place with the mechanical loading, okay, hydromechanical loading. So you can see there's quite a difference. That's the same material under the same strain. It's just the measurement that's different. One's measured with strain gauges, the other one's measured with ultrasonics. And so you see quite a difference in the bulk modulus as computed from that. So you really have to understand what's going on there. And this is sort of easy to understand if you think about it. Well, let's wait, I'll talk about it. Okay. Also, this is just another example of the frequency dependence. So this is on the left where it says log, okay? These are measurements taken at frequencies that correspond to sonic logs, like what you'd use in the field, the sonic logs have frequencies on the order of kilohertz, right? And over on the right, then you have measurements taken in the laboratory with ultrasonics, which have frequencies on the order of megahertz, okay? And you see that the sonic velocities measured are, so on the top here are the pressure wave, and on the bottom are the shear wave. And you see that these have a functional dependence upon the frequency at which the measurements were, the excitation was done, okay? And you see that, you know, the shear wave has a lower frequency dependence than the pressure wave, okay? And this is pretty typical in that you'll see this sort of limiting case. So on the lower end, you have a plateau, and then there's some transition frequency range, and then you sort of have a plateau on the upper end, okay? And what this is a transition between sort of two types of behavior, and those two types of behavior we call the drained and undrained behavior, okay? So this is specific to a poroelastic material, and if you read in chapter 3, he talks about this, you know, SQRT or SQRT theory, and this is pretty easy to understand actually if you just sort of use an idea. So, you know, fluid diffusion is a slower process than wave propagation in an elastic, you know, media, right? So, if you have a rock and you squeeze it rapidly, okay, if you squeeze it very rapidly, so fast that the fluid doesn't have time to diffuse through the pore system, then you get an immediate increase in pore pressure due to the immediate loading, and the fluid doesn't have time to sort of squirt out, right? So in that case, you would measure a higher bulk modulus because you're loading it faster. You're loading it really quickly, the fluid doesn't have time to escape, and so you measure a stiffer, you know, you measure something that's stiffer, okay? And in this case, it's called the drained limit. So when we talk about geomechanics, a lot of times we use these things that are called drained and undrained. So I'm sorry, what I was just describing is the undrained case. So in the undrained case, you can think of that undrained like fully saturated, right? So undrained, fully saturated, and the pore pressure affects the solid deformation, but the solid deformation doesn't affect the pore pressure because the pore pressure doesn't have time to change because it's a slower process than the solid deformation, okay? And the opposite of that is the drain case. This would be a very highly permeable media or slow loading. So, and this is just the opposite case. So now I'm going to load something very slowly, such that the fluid does have time to diffuse away. And in that case, there's not an appreciable change in the pore pressure. So in that case, it doesn't affect the solid deformation very much. Okay, so these are sort of the two opposite ends of the spectrum. In one case, fluid can't diffuse, and the solid deformation is affected a lot. And in the other case, fluid can diffuse, and the solid deformation is unaffected by that, by the pore pressure change. Okay, and so this is what you see in these plots. So remember, when you're with sonics and ultrasonics, you're vibrating it. You're propagating an elastic wave through it, right? And even though you can't see it, it's straining the material, right? I mean, that's obvious. If you put your hand on your car while it's running, you feel something, right? That what you feel is the motion of the car, and it's very small strains, right? So when you propagate a wave, you're elastically deforming it, a tiny amount. You know, you'd never be able to see it, but you're deforming a tiny amount, and the frequency of that wave affects how fast you're loading it. And then what you see is this transition from the undrained to the drained behavior. And that's why these two kind of limiting plateaus are in the frequency response. So a couple other effects of viscoelastic materials, okay, are creep and stress relaxation. So creep is when I load a material to constant stress and then I hold that stress. So I load the material and I hold it. If it continues to strain, that's called creep. A lot of materials exhibit this. Stress relaxation is sort of the other effect in that I'm going to strain a material and hold it at a constant strain, and the stress will relax. Okay. And so here's an example. So this was some tests done on some dried sand. Whenever we talk about testing materials dried, that means that they've typically been baked such that the hydrocarbon residues eliminated from them. So here's a dried sand in which a series of creep tests were done. So the kind of darker squared off lines are confining pressure. So the sand was placed in a jacket in a bath of water, and the fluid pressure was pumped up, and then the strain was measured. Okay, so you pumped up the fluid pressure, and then they hold it fixed, and you measure the strain. So the fluid pressure is being held fixed here, and the material continues to strain. Okay, and then it was briefly unloaded, reloaded to a higher pressure, and held fixed, and the material strained. And this, continued through every loading cycle. Okay, so that's an example of creep. We can come up with lots of constitutive laws. One that happens to work really well is a power law, and I think you should, you should be able to notice that, right? If I have a function that's like, in this case, a function of time, right? If I have some constant times time to some power, I get this kind of curve, right? I mean, qualitatively, that will look like that, right? So I can fit this behavior relatively well with a constitutive model that looks like this. So some initial strain, epsilon 0, plus some constant times time to some power will give me a curve that looks like that. And so then the constant and the power are, fitting parameters. So you fit the constituent, you do, say, some least squared regression or something so that your model best fits that curve. And then you can use this type of model to predict how much material will creep. So stress relaxation, this actually shows two effects. One is stress relaxation. The other is also rate dependence in the elastic moduli. So you can see here the strain rate at 3 decades of strain rate. So 10 to the minus 5th per second, 10 to the minus 6th per second, 10 to the minus 7th per second. That's still pretty slow. But you can see that the elastic moduli increase. So the elastic moduli increase as a function of loading rate. So this is the slowest loading rate, and then you go to the next highest and the next highest, right? Here's also been plotted as a function of confining pressure. So in this case, it's a triaxial test where like a sample has been, a sample like this is put in a bath of confining pressure. So a hydrostatic confining pressure of 15 MPa, and then it's squeezed from the ends mechanically, okay? And then the response is measured. And so you can see that not only is the material rate dependent in the sense that the faster I load it, the elastic moduli goes up. It's also pressure dependent. So the faster I load it and the higher the pressure, the elastic moduli goes up. Okay? So then in this case, the test was strained and then held fixed at this point, and then the stress is measured over time after that, and you can see the relaxation. And you can see, the relaxation is also different depending upon the rate it was loaded. So now we're getting away from purely elastic behavior, right? Because in an elastic material, you load it and you unload it, and it goes right back where it was, right? Along the same path. So now we're starting to look at some effects of inelasticity. And in this case, the materials are still elastic. I mean, that's I shouldn't say inelasticity. The materials are still elastic. They'll still go back to zero stress, zero strain. It's just the path that they go back along is not along the same path that they were loaded. Right? So there's some hysteretic effect. Okay. Yeah.
There's no deformation if we get past that strain when it actually goes
So in here, what you're seeing in stress relaxation is you're deforming it and you're holding the deformation fixed. So the deformation doesn't change. It's the force. So what it is, okay, I take my rock and I squeeze it with my hands. Right? I'm really strong. I squeeze it and I deform it and I hold it. And over time, how hard I have to squeeze it, the force I have to apply to hold it at that constant strain over time goes down. So I don't have to hold it, I don't have to push as hard over time. This is the effect of stress relaxation, right? And using the same analogy for creep, there I squeeze it and I hold the force at which I squeeze it constant, and then my hand begins to continues to move over time. So it continues to deform. And so that's really what we're going to cover in terms of poroelasticity. And then, we can also add thermal effects. Of course, in reservoirs, we have appreciable temperature effects. And so there you have an additional term, additional elasticity. So here you have, and I'll correct this in the notes just to be consistent with what we had before. This is S, right? S minus the effect of pore pressure minus the effect of thermal strains, okay? So here you have the bulk modulus, K, and then you have this coefficient of thermal elasticity, okay? So this is something that you would measure in the lab. You'd go in the lab and you would have a sample and you'd heat it up, and the sample would deform, okay? And so that the ratio of change in temperature to change in length is this thermal elasticity constant, okay? And so that would add in the effects of thermal elasticity. That's a carryover from the previous slide, okay? So that's what I have for today.